You can share your screen, Rajaram. We are already online on YouTube.
So, tell me when.
Yeah, we can start. You want to make some remarks before you share? Yeah.
Yeah, it's on record. It's being recorded. Yeah.
Yeah, Shilkumar, you can also start the Zoom recording.
Yeah.
Yes, please. Go ahead.
Okay. So the previous talk, lecture 4, was extremely focused, I would say. Just entirely pursuing the theme of closure quantities to their logical conclusion, even for full polar observations. Now, in contrast, this lecture has the following spirit. It's as if we have been on a kind of journey, a reasonably targeted journey through topics in polarization of some relevance to radio astronomy or optics. And but on the way, we've encountered various interesting things. I've remarked on them, but not really gone into them in any great depth. So the purpose of this lecture is to pick up these different topics. They are somewhat interrelated, but they're distinct topics, I guess, and go deeper into them. And naturally, it will involve some more mathematics. But ultimately, if you think about it, it's all about 2 into 2 matrices, okay? Or 2 into 1 or 1 into 2. So anyway, let's go ahead. And, so this is the slideshow, and we'll start from the first slide. Mind? Okay. Right. So one topic which I'd like to explore is representing on the Poincare sphere what happens to the state of polarization, because that's all that the Poincare sphere can show you. When you have absorption or loss in radio terms, this is motivated originally by the optics of absorbing crystals, which was pursued by Pancharatnam and RRI. But it's a general question which one would like to answer. Turns out this is connected with Lorentz transformations. And in fact, the analysis will parallel some of the analysis we did in connection with closure quantities in polarized observations. Then we touched upon the problem of adding phase back to the Poincare sphere. Okay, and in a simple-minded way, you would say each point on the Poincare sphere now has to become a circle. and this two-dimensional object has to become a three-dimensional object. But exactly what kind of three-dimensional object, how these circles sit in it, and in particular, how they manage to sit in such a way that you're unable to have a surface which cuts all these circles and is itself smooth, right? It runs into problems somewhere. I mean, we already saw that, but the deeper geometric reason hopefully will come out in this talk. And the other problem, which I mentioned, in connection with the polarization of the sky, and it could also be the polarization of the CMB for that matter, is that if you just stick to linear polarization and you try to create, say, an X and Y kind of frame at every direction, in either coming in all directions or propagating in all directions, it encounters some interesting obstructions. I think we discussed this theorem, which says that's not possible, but I'd still like to go a little deeper into it because that has some interesting aspects. Okay, I'm not seeing the slide change. Okay. No, I think it was just a bit. Right. So before talking about loss, let's talk about losslessness. Yeah, I haven't, I should have made these appear in sequence, but never mind. So once you're lossless, the transformations of polarization preserve intensity. So if we have these two complex numbers, Z1 and Z2, it preserves the absolute value of Z1 squared and the absolute value of Z2 squared added, or Z1, Z1 bar, Z2, Z2 bar. Okay. And therefore, this matrix which transforms them, you can either think of it as a passive transformation, that is, the light remains the same, but you just decide to describe it differently, and you would like the new description to give you the same intensity. Or this light could be propagating in some medium, and its polarization could be getting transformed by this matrix. So in the case of a lossless situation, you have a unitary matrix, which is defined by the product of U and U dagger being the, okay, I shouldn't have a plus on the identity matrix, though it doesn't matter. Now, this immediately tells you that the determinant of this matrix has to be a complex number of modulus unity, so exponential I alpha, and that will turn out to be relevant. Okay. Now, the Stokes parameters transform in this way, which you can readily see if you think of the Stokes parameters as defined by the product of a column vector and a row vector on the right, representing the same electric field. So now we are not talking of two different antennas, okay? We're just talking of one incoming fully polarized electric field, okay? So then the one on the left transforms to the U and the one on the right transforms to the U dagger, and this is what you get, okay? And this automatically guarantees that the determinant of this Stokes parameter matrix, capital S, is preserved. Now, a general 2 into 2 complex matrix has 4 real parameters, okay? But U is not just any old matrix. The rows of the matrix have to satisfy the condition that they are normalized and that they are orthogonal to each other. In fact, that follows from this earlier condition, U dagger equal by 2. So when you impose these conditions, you find that you are left with 4 real parameters. So one could say that all the possible lossless transformations, linear transformations, of course, of polarized light will have 4 parameters. But when we go to the Poincare sphere, we are not interested in the overall phase. In fact, we can't represent it, right, on the Poincare sphere. So then you can put a further condition, one more condition, that we can change this matrix so that its determinant is unity. So remove one parameter essentially. So then you will be dealing with unitary matrices, 2 into 2 with determinant unity. And now you will have 3 real parameters. Okay. Now, there's a nice shortcut to saying what the corresponding transformation will be on the Poincare sphere. It's not completely obvious because the passage from Z1, Z2 to the Poincare sphere is kind of nonlinear. You first divide by Z2, then you do stereographic projection, etc., etc. But now that we know that the Poincare sphere really has Q, U, and V living on it, okay, then one can use the property which we used in our discussion of closure quantities, that this kind of transformation preserves the trace, because U dagger is U inverse, right? So it preserves the trace and the determinant, okay? Now the trace is I, okay? But I is not what we're worried about in the Poincare sphere, right? Anyway, that's set to 1. And the determinant is I squared minus Q squared minus U squared minus V squared, okay? So therefore, the sum of these 3 squares is preserved, right? And that is a powerful constraint, right? It has to be rigid rotations in the QUV space. And since QUV are coordinates on the Poincare sphere, it's a rigid rotation of the Poincare sphere. So these lossless transformations are rigid rotations, and it's pleasing that they also have 3 parameters, right? If you think about it, 2 parameters to give you the axis of rotation, and 1 parameter to give you the angle of rotation. So that is as far as lossless transformations are concerned. However, if you look at general transformations, general linear device, we saw that it had 8 real parameters. Okay, and we also talked about how these transform, right? It's multiplied by G and G dagger and so on. Again, for our convenience, we can take the determinant of G as 1, right? And interestingly, for a general matrix, this has actually 2 conditions, because the determinant G is in general complex. It's not modulus unity. Okay. So we are left with 6 parameters. Now, our lossless devices only account for 3 parameters. Okay. So if we want to include absorbing crystals or lossy devices, we need 3 more parameters. And we don't want to reinvent the rigid rotations, right? So now, because I square minus Q square minus U square minus V square is preserved even in these general transformations with determinant 1, that's what we discussed in our discussion of closure quantities. So they are Lorentz transformations. But now general Lorentz transformations. Actually, the rigid rotations are also Lorentz transformations, but they don't involve going to a moving frame of reference, just a rotated frame of reference. Okay. But now, once we include lossy systems, we have to go to a moving frame of reference. Now, from our knowledge of Lorentz transformations, we can readily see that will give us the 3 extra parameters which we need, which in the relativity literature, they're called boosts. That is just going to a moving frame with some speed in 3 different directions. Okay. Now, I'm just trying to see how these pan out on the Poincare sphere. So we don't want to revisit rigid rotations. Okay. So as a particular example, let's keep the V-axis fixed. And we also do not allow Q and U to rotate. So I'm just stating that you have the single parameter Z, which is the ratio of Z1 to Z2, right? And I'm saying that the only thing which seems to be allowed is to multiply it by a real number. Now, there's a bit of a leap here. So let me expand on that. Right? Once you do not allow Q and U to rotate, it means you have to travel along a line of longitude on the Poincare sphere, right? You're not allowed to, yeah, that's right. You're not allowed to change that phi angle at all. So then, under stereographic projection, that line will project to a line through the origin of the complex plane. And that is exactly what's going on here, right? And further, we now know that the theta angle on the Poincare sphere measured from the top is going to get multiplied by this. I mean, cot of half theta is R. We saw that geometric relation. between distance from the origin on the complex plane and angular distance from the pole on the sphere, right? So we have completely pinned down this transformation. You cannot change the phi angle, whose physical significance is the azimuth of the polarization. You're not allowed to change that. But you can move along the line of longitude, and you multiply cot half theta by r. Now, there are 2 points which are left unchanged by that. Okay. So one is the North Pole, because cot half theta is infinite there anyway, right? So you can multiply by r, will remain infinite. And likewise, the South Pole, where cot half theta is 0. So this transformation, which we are talking about, leaves, let us say, right circular and left circular unaltered, but it changes the proportion of right circular and left circular, right? I mean, if it didn't even do that, then nothing would be happening, right? And the way it changes the proportion is that all points on the Poincare sphere, other than the 2 points we talked about, will move along the line of longitude. And the law according to which they move is clearly stated here, right? So, for example, if there was a point in the upper hemisphere, right, which had cot half theta equal to 2, right? Or let's say a point on the equator, which had cot half theta equal to 1, and you wanted to double it. So it would go to cot half theta equal to 2. Meanwhile, the point with cot half theta equal to half in the lower hemisphere would come to the equator. So that's the kind of movement which you have. So you can think of it as a kind of flow along the line of longitudes. And this is clearly not a rigid rotation, right? In fact, this has a name in optics. It's called circular dichroism. Dichroism simply means that the two well, actually, it's strange because this has nothing to do with color, but what it really means is that the two circular polarizations develop an amplitude difference as they propagate, even the relative amplitudes. So we are ignoring overall absorption, which is common to the two polarizations. And we are saying you could have a medium in which one of the circular polarizations is more absorbed than the other, right? But they are still eigenstates, right? So if you took that original matrix, which represents this, and you would find that these are eigenstates, but the eigenvalues, would be two different real numbers, okay? Interestingly, circular dichroism is a very popular tool in biology, because all biological molecules, have a handedness, right? So most of their absorptions are in ultraviolet. So you can go to the net, and if you want to buy a circular dichroism spectrometer, you will find it being offered. And I just did some Googling just for fun, and I found that this is very popular in IIT Bombay and IIT Delhi. They are central facilities. So this is not completely theoretical exercise. In any case, now that we have one of these transformations, we can get two more, because we can just do the same thing along two different axes of the Poincare sphere. For convenience, we did it along the vertical direction. Okay. Now, of course, I'm calling it Lorentz transformation for purely mathematical reasons, right? However, it turns out that it's actually related to a physical Lorentz transformation, because one can ask a completely different question. Okay, so forget polarization. So you're sitting wherever you're sitting, and you're receiving radiation from all directions, right? So the direction of your incoming radiation is the celestial sphere, the map of the sphere. And then you decide to start moving along the z-axis, okay? And this is certainly something which people in radio astronomy are very familiar with. It's called relativistic beaming. Of course, there you're emitting radiation rather than receiving it, but the idea is the same, right? So if you start moving along the z-axis, you will find that the angle of everything to your direction of motion will change. Everything will be, whatever is coming from the forward direction, right, will get more and more concentrated into a smaller and smaller solid angle. And that's exactly what is happening in this case, okay? And one shouldn't be surprised. There's a remark which Feynman, I think, makes repeatedly in maybe volume 2 and maybe in other places, he says the same equations have the same solutions. Okay. So in this case, the equations which governed motion on the Poincare sphere happen to be Lorentz transformations because of preserving I square minus q square minus u square minus v square. And of course, the equations which govern the direction of radiation which you receive as you move also preserve that same combination. Okay. So now this transformation, which is of course, again, all astronomers should be very familiar with it because it is discovered by an astronomer. It's called aberration. Okay. And it's a pretty brilliant experiment if you think that it was actually done in 1695. Again, Reverend Bradley or something. And it's, of course, today it's a huge effect. It's 20 arc seconds, right? But to do it at that time, he actually did something clever. He had a telescope which didn't have any kind of mount. It was just fixed. And it was pointed upwards when the sky was clear. And he could wait 6 months when the velocity of the Earth changed and actually measure this. Okay. So that's the connection with the celestial sphere. Now, I've shown on the right crystal of amethystine quartz. This I took from the net, but in the days when I was in the Raman Institute and went around the museum, it's full of beautiful samples of this. And at least some of them must have been studied by Raman and Pancharatnam. Okay. Now, of course, we have just talked of one transformation, right? This circular dichroism. But in reality, if you, in that given direction, the crystal might have different absorption for two polarizations, but it might also have a different refractive index. Okay. Now, so it will be a combination of whatever we talked about with a rigid rotation. Okay. Now, at least in the case that we discussed, you can see that if that rotation is along the v-axis, okay, and if things are also being pushed along the longitude, you will have a kind of spiraling motion on the Poincare sphere. Will still actually preserve these two eigenstates, right circular, left circular. Okay. There are nice diagrams illustrating all this, which will be there in one of the references I put up. Okay. So that's the sort of easy case. But the more interesting case and the general case when you get into an absorbing crystal is that on the one hand, the two eigenstates might be, let's just say circular, as far as absorption is concerned. But as far as mutual phase shift is concerned, the two eigenstates could be something else. So now you have to combine the rotation about, let us say, the u-axis and this kind of Lorentz transformation, everything trying to creep up to the North Pole. Okay. Now, you can just write down that matrix and diagonalize it. That's one way of doing it. And the other way is to actually sketch these vector fields on the Poincare sphere. And what happens, as you might guess, is that these 2 points where which don't move actually get shifted. But what's really interesting is they get shifted in opposite directions, so they are no longer opposite. Now, the physical consequence of this, which is what I've written down here, is that you have, normally when people study crystals under the microscope, they first have a polarizer, right? And then they have an analyzer, which is usually put to annihilate that polarization. So your field is dark. And then when you stick in the crystal into your thin sheet of crystal into your microscope, if it transforms the polarization, incoming polarization, now something will be let through. Okay. And since you might be seeing things as a function of direction, if you focus the microscope down on the sample, you'll be collecting things in the image which propagate in different directions. So if this phase difference is different in different directions, you'll get fringes. So that's the traditional way of doing it. But as pointed out in these classic papers by Pancharatnam, in the kind of situation we are talking about, where the two modes are not opposite points on the Poincare sphere, what happens is, first of all, you can send in unpolarized light, okay? And then it can be split into a combination of these modes. Okay. And then the relative weight of these two modes changes as it propagates in the crystal. Okay. So now the light will no longer be unpolarized, number one. And number two, because these modes are not orthogonal, they will show intensity interference without an analyzer. As it turns out, these absorption effects are not that strong. Okay. I mean, one simple way to see it is you could get an absorption of the order of 1, e raised to minus 1 in the exponent, right? Maybe with, a millimeter of crystal. Okay. But a phase shift of the order of 1 will occur in, a fraction of a micron, right? So the absorption effects are weak, but in spite of that, you actually can see weak fringes, right? So that's an interesting point, that you can just put unpolarized light, don't use any analyzer, and you may still see fringes. And I think that's what attracted their attention to this class of problems, on which some very nice papers were written. I've only talked of one of them, but it's an entire series to which I will put up the references. Now, one interesting case, you might say pathological case, is that these two modes, which were originally orthogonal, actually merge. Okay. Now, can that happen? Let's go back to the algebraic way of looking at things, where we have this matrix, which is transforming Z1 and Z2. And okay, it's a general matrix. It's no longer a unitary matrix. And a general matrix will have two eigenvectors, but they will not be orthogonal. That's well known from matrix theory. But what is known, of course, in matrix theory, but maybe we're not very conscious of it all the time, is that sometimes these two eigenvalues can merge, eigenvectors can merge. Okay. So then this matrix only has one eigenvector. It's something called a Jordan form. Okay. But in physical terms, what it does is the paths which polarization now takes on the Poincare sphere are such that no other point is fixed. Only one point is fixed, that one eigenvector. So this was, it was noted in the early days of crystal optics, but there was some confusion about what would happen if you sent in, say, the orthogonal polarization. Would it get reflected and so on? And that was brilliantly clarified by Pancharatnam. I will actually give the answer to this question right at the end, because it turns out that this is related to something else that we're going to talk about. Okay. Well, I've already sort of given it away, that you have this single point, and the paths which the polarization takes on the Poincare sphere look like dipole field lines. Okay. So now, for completeness, I should also say that something which one probably should not be representing on the Poincare sphere is depolarization. Okay. Now, of course, it's true that the original work of Stokes was already considering a form of depolarization. So on the scale less than the inverse bandwidth, you had a very well-defined polarization. And then when you averaged more and more of such coherence times, you either got complete depolarization or partial depolarization. So that by itself is not something new. However, it can also occur in the context of radio astronomy, because your beam always has a finite size. You're looking at some region, and let's say you're looking at polarization, and this is coming from synchrotron emitting plasma, which means there's a magnetic field, but things are at different depths in the magnetic field. So they get rotated by different amounts, and you get depolarization. Okay. So in fact, there's very nice work on the galactic background at very low frequencies from Westerbork, which showed that what looks like a very dull image in I becomes quite an exciting image in Q and U. Okay. So depolarization can occur because of this kind of averaging, right? Not averaging over some kind of beam. And in the laboratory, it occurs if light passes not through a single crystal, but a polycrystalline aggregate. This problem was attacked as part of his PhD thesis by my NAL colleague, Professor G.S. Ranganath. Okay. Now, it turns out that in this case, yes, before you have the depolarization, you could certainly represent the transformation of the Stokes parameters by putting some matrix to the left and the adjoint to the right. So this is the so-called Jones way of doing things. But now you are going to average over this matrix. Remember, we always kept the matrix outside the averaging sign. But now you have to put it in the averaging sign. And then the final result cannot be represented in this way. So then what one does is, but one can do that in general, but it really helps in this case. You only look at how the Stokes parameters transform. After the averaging over many coherence times for the electric field and averaging over the different transformations which different parts of your observed light have undergone. Okay. So this is a formalism I've not talked about at all. You just put all the Stokes vectors, IQUV, into a column vector and see how they transform. Now everything is real, which might be a comfort, but you have 4×4 matrices. And in all the cases we've discussed so far, they can be done with Miller matrices. Somewhat to my surprise, I found Miller matrices in the classic papers of Hamaker, Bregman, and Salt. Actually, it turns out that, and I should have realized this, the Dutch have a very strong tradition in optics, and maybe going back to Huygens. So that paper repeatedly tells the radio astronomers that, here we are coming to you with all this technology that we know in optics. So they put this in as well. So that's as far as absorption and depolarization is concerned. Now, I guess I have to give the statutory warning that there will be a certain amount of graphic content in what follows. This is where I'm going to try and take you around this three-dimensional object in which the Poincare sphere lives. Okay. And I've taken this from another talk, and therefore you no longer have this black and white effect. Well, Cartesian duality is mind and body. So, but what I have in mind is what I consider Descartes' greater contribution, which is x and y. Okay. So on a plane, you can assign an angle theta and height z. Okay. But if you try to do this on this Mobius strip, the theta you can assign, right? But let's say that I say this point has a positive z, but I come around, I'll find it ends up with a negative z. Okay. So the practical solution is to divide this into two regions and give one coordinate system in each region and give some transformation which happens in the overlapping region. Okay. But it's interesting that you have this thing where you're not able to introduce a global coordinate system, even though locally, and locally means even quite a large part of this Mobius strip. In fact, if you just cut out a tiny portion of the Mobius strip, so that it's not allowed to join itself, you'll have no difficulty in assigning x and y coordinates. But when you look at it as a whole, you're not able to. So one way of stating this is that it's locally a Cartesian product. And the word Cartesian product is precisely because Descartes took the Cartesian product of x and y, right? But it's globally twisted. Now, this kind of mathematical object was actually studied even by Clifford in exactly the example we're going to talk about. But as a general theory, it happened in 1930s, 1940s. And of course, it continues to be part of mathematics today. Right? And the one that we are interested in is the one where we include the phase of polarized light, but we still don't worry about the intensity. Okay. Okay. So if you, I have represented three coordinates here: Q1, P1, and Q2, and I have suppressed P2. The reason I have suppressed P2 is it's number one, it's hard to do 4 dimensions. I can kind of draw in 2 dimensions and help you to imagine the 3rd dimension with using dotted lines and all that. And the second reason is that our intensity is constant. So think of Q1 and P1 as the real and imaginary parts of Z1, Q2, P2 as the real and imaginary parts of Z2. And the sum of their squares is 1. So P2 is either the negative square root of this quantity, 1 minus sum of 3 squares, or the positive square root. Okay. And of course, so you can also think of P1 and Q1 as the momentum and coordinate of one of these harmonic oscillators. Okay. So then this is just the energy being one. Now, just as we are free to, subject to total energy, we are free to put more energy into one of the oscillators than into the other. Right? So P1 square plus Q1 square can have any value. Likewise, Q2 square plus P2 square. But the values have to add up to 1. Okay. So the fact that the sum of these 4 squares is 1 means that fundamentally the geometrical object we are dealing with is a 3-dimensional sphere living in 4 dimensions. Okay. Or S3. Now, we have faced this problem even with S2, the Earth on which we live. And to make maps of it, of course, if you there is stereographic projection, but if we stay away from that, we can make a map of the northern hemisphere, we can make a map of the southern hemisphere, and then say that our Earth is just obtained by attaching these 2 maps at the equator. So we're going to do something similar. So if you take the positive square root, that's this hemisphere, except, it's a solid sphere, so to speak, right? Because this still has 3 dimensions. Okay. So we're faithfully representing the 2 real and imaginary parts of one of the harmonic oscillators. But we're representing Q2, and you just have to understand that, for example, if Q2 is 0, then at this point, P2 is a maximum. And then when Q2 reaches its maximum value, then P2 is 0. So P2 is 0 on the surface of this sphere, and likewise on the surface of this sphere. So that's like the equator. But in S3, the equator is itself an S2. Just like in S2, the equator is an S1. Okay. Now, let us represent. So let's say we are in a circular basis, for example. So let's represent the 2 extremes. Let's put all the energy into oscillator number 1. Okay. So P1 square plus Q1 square is 1, and both P2 and Q2 are 0. Okay. So if Q2 is 0, that means you're in this horizontal plane. Okay. And then if P1 square plus Q1 square is 1, then you are on this circle. Okay. And this actually lives on the equator, so to speak. Right. And of course, because this sphere represents the boundary between our 2 halves, okay, the same circle is being drawn here. Right. So the surface of this solid sphere is the same as the surface of the solid sphere, but of course the interior is different. Okay, that's as far as one of the oscillators is concerned. Now suppose we go to the opposite case, where P1 square plus Q1 square is 0. So now in the P1 Q1 plane, we are at the origin. So then it's only Q2 which has to oscillate between -1 and +1. Of course, P2 is also oscillating, but we have to just infer that, right? That when Q2 is here, P2 is a maximum. And likewise, P2 is 0 at this turning point by the oscillator. Now, this is clearly a circle, right? When we had just all the energy in oscillator number 1. But this is also a circle. I mean, that's something you have to get used to, right? That it starts from here, goes here. Okay, let me go back. And then it actually enters the other hemisphere. It's crossed the equator, so to speak, right? Then goes in the opposite direction. Because we actually said P2 had a maximum value here, right? And now it has that negative maximum value here. Okay, other way around. Had a positive maximum value here and a negative. So please do think of this as a circle, because this point is glued to this point, and this point is glued to this point. So every I mean, I've shown you that these two extreme states, the North Pole and South Pole of the Poincare sphere, are circles living in this S3. But everything else is also a circle, because what can a harmonic oscillator do? It's pretty repetitive, right? Just comes back to the same values of P1, Q1, P2, Q2. Of course, in that case, both the oscillators are excited, but they have some phase relationship, but that phase relationship doesn't change because they have the same period. So now I'm going to sketch an intermediate case where there's some energy in the number one oscillator, but not the full amount. So it's going to move in a circle, which is not radius 1. And likewise, the two oscillator will oscillate with an amplitude which is less than 1. Okay. So now we have this, instead of having this line on the axis, it's now become a little fatter, right? Because we have the number two oscillator has given some energy to the number one oscillator. And now, of course, both P1 and Q1 are oscillating. So if you look at the projection onto P1, Q1, it'll be a circle of a smaller radius. That's what we're saying. And if you look at the projection onto Q2, it's back and forth. So this is what it looks like. For example, you start from here, come here, reappear in the other hemisphere, come back. So this is a circle. And what does it live on? One is tempted to say a cylinder, but the cylinder doesn't really have a boundary, right? Because, sure, it crosses this hemisphere and then it's attached here. Then it comes back here. So this is actually a torus. Okay. So it turns out that except for these two extreme cases where all the energy is in one oscillator, any intermediate case, these circles, this is a circle. I mean, it's fairly clear this is a circle, but it's not the only one living on this torus, right? Because you could have started out with a different initial phase for these two oscillators. Okay. So here I've started with a different initial phase. So sure, it'll cross the equator at a different point, but it's also a circle. So you should really think of this torus as filled with these circles. Okay. So now I can try and illustrate why one might have a problem in creating a global phase convention, which means finding a surface which intersects all these circles once and only once. So I've gone back to the first figure. So let's say we pick a dot on this, right? And then we take a surface which intersects this particular orbit at that dot. But the surface is small. Think of it as a small horizontal surface. Now, of course, it's also going to intersect the remaining tori, right? So again, if I go one step back, if you think of the surface which originally intersected the axis of the cylinder, it now might expand to some curve like this. It doesn't have to be exactly like this, but topologically, it'll be like this. Okay. Right. Then it can keep expanding. Right. But now what's going to happen when the torus collapses? It'll have to fill this whole surface. Right? So, as I said, we started with a small piece of the surface, cutting this vertical line. It expanded to a circle on the torus, which became like this. And the surface bridged it, still intersecting every orbit only once. But now, the last orbit, it essentially collapses onto the whole orbit. It doesn't intersect it at one point. I think we encountered this when we tried to extend the Pancharatnam phase convention, but this is how it happens purely topologically. I realized that my diagram is a bit inadequate. Okay, what you'd really like is, someone who can show you all these tori so that they look like toruses. Tori. Okay, it was beyond my powers of illustration, which is why I went to these two hemispheres. But fortunately, it's not beyond the powers of a very illustrious illustrator, none other than Roger Penrose. So I think Penrose has this thing that he draws all the diagrams for his books. The only other person I know who did that was George Gamow. Okay. So I'm now going to show you, and he's not going to split the S3 into a northern and southern hemisphere. But how is he going to represent S3 in our normal three-dimensional space? We also have a hint of that. because we represented S2 on a two-dimensional plane by stereographic projection. So you can do the same thing for S3. So let's say you live at some point on S3. In fact, you might be living in a closed universe, right? So then you can draw bigger and bigger spheres around you. And the coordinate which labels these spheres is like some theta axis, how far away you are from the pole. And then the spheres become bigger and bigger until they reach the equator, and then they shrink to the opposite pole. Okay. But what happens when you do stereographic projection is one of the poles gets blown up to infinity, right? So that price you do have to pay. But therefore, you do have the advantage that you are not, patching up things between two representations. Okay. So here is Penrose's diagram. Okay. And you may ask, why did he have this? For his own reasons. With Rindler, there wrote two volumes called Spinners and Spacetime. Now, you could be intimidated by these spinners, but actually, we have been talking spinners all the time without calling them that. Maybe I'll say a little bit on that at the end. So now you can see this torus which surrounds that circle. And then the other circle is this axis which he shows, right? So now you can see it much more vividly. Here are all these orbits. And here is the surface which cuts them. So it can get bigger and bigger on this fat torus. And then the tori shrink again. But so you can draw a line cutting all these where the surface cuts this torus. But that will completely fail when you come to the core of the torus. Okay. By the way, this can also be given a formal geometric proof. But anyway. Okay, so that's, as I said, this was in another context, in a talk given in ICTS, which is also on geometry and topology and optics, but catering to that audience. So I borrowed those slides from myself, except this is borrowed very much from Penrose. So now I want to come back to this idea of representing linearly polarized. Actually, if you can represent one linearly polarized field, you can represent the other by just drawing a little bit perpendicular on the whole celestial sphere, which we know is impossible, but let's see where things go wrong. So here is linear polarization. I'm transferring it from the pole. So let's say we're looking at the north pole of the sphere. So we're only looking at half the sphere. Okay. I'm transferring it along a line of longitude. Okay. And trying to keep it parallel to itself. Now, the geometric statement, which is often used in GR textbooks, is that there's an operation even on a curved surface called parallel displacement. So intuitively, it's as if you gave a horizontal pole to someone who lived on the sphere, and you told that person to walk down to the equator along a line of longitude, holding the pole horizontal, but keeping its angle with his trajectory constant. In this case, the angle is 0. Right? And I'm also drawing these smaller and smaller, not because the pole is shrinking, but because we are viewing it from a more and more oblique angle as it approaches the equator. So at this point on the equator, the pole is clearly pointing towards you, right? But at this point, if you move along this line of longitude, you can see that it makes that constant angle with this line of longitude. So what you end up with is a situation where you wanted to transfer this linear polarization all over this hemisphere by this operation of parallel displacement. And when you did, nothing terrible happened. But on the horizon, at some places that direction was vertical, and at some places that direction was horizontal. Actually, you would do this very intuitively. If you just stood and held a pencil over your head and then moved it down to different points on the horizon, you'll find that if you moved parallel to the pencil, you would end up with something vertical. And if you moved perpendicular to the pencil, you'll end up with something horizontal on the horizon. So already on this equator, we find this interesting phenomenon that you've successfully transferred the polarization, but it's not what you would call parallel on the equator. So I'm representing that by some kind of field lines. Okay. So instead of drawing all these double arrows, I'm representing it by these field lines. But things get really interesting when you go to the other hemisphere. Okay. So you just extrapolate these field lines. I mean, you follow the same rule. You keep walking. So maybe one good way to imagine it is that this pole was given to a large number of people, and all of them were asked to walk along longitude, and they were asked to meet at the opposite pole. And you can guess that when they meet at the opposite pole, each one of them will be holding their pole in a completely different direction. In fact, here it rotates by 2 pi, and by the time you come there, it'll rotate by 4 pi. I've tried to sketch those field lines on the back. So this is like the dark side of the moon. So this is the other side. Now, of course, the one who went parallel to the polarization goes through. But for example, you have to accommodate the horizontal line. And this point is a kind of singularity. The direction is not well defined at all. Now, what I find very nice is that this pattern of lines, okay, can be thought of in at least 3 different ways. So number one, it's the kind of field lines which result when you try to transfer polarization from one pole all over the sphere along lines of longitude. Now, one can ask, is this a fictitious field line, or is there any source which will actually generate these field lines? Well, the answer is that at the North Pole, if you placed an electric dipole and a magnetic dipole, okay, so maybe I'll go back. Yeah. So suppose I had a magnetic dipole. So these are now physical objects. Or, I mean, you could put them at the center of the sphere. And in this direction, let's say that's how they radiate. And the nice thing is, if you had only the electric dipole, the field would vanish, or the 2 axes. But because you have this magnetic dipole, the field will not vanish. Okay. In fact, the field will not vanish anywhere except at a single point, which is at the back. And those field lines are exactly the same as these. In fact, you can construct these lines by taking a sphere and just intersecting with the plane. So if the plane, one position of the plane, it will intersect along this great circle. And then if you tilt the plane, it will intersect it along small circles in both directions. So that's the geometry of these lines. And it's the same as the singular case of the Poincare sphere. Okay. So there's 3 uses for this diagram. So the case which was investigated by Pancharatnam, where there was only one eigenvector for this non-Hermitian matrix, lossy matrix. Right? In the case it had only one eigenvector, and you put in a general polarization, this is how it would move the Poincare sphere. Okay. So you can agree that I've taken you in some fairly recondite directions, but basically following one's nose, just asking reasonable questions about polarized light. Okay. So thank you.
Thank you, Rajaram. Yeah, a lot of food for thought, I guess. Yeah.
Yeah.
And,
okay. And the question is, how long it will take to digest?
Yes.
The food analogy, but yes.
Yeah. Okay. Of the folks online, any questions? And while I'm trying to go to the YouTube.
No, just a request for some reading material.
Yes.
I think the material is quite dense, and I think it will take a while to wade through, and particularly the visualizations will take more time.
If you found it dense, then I would definitely agree. But maybe, throwing this out, and I'll definitely put up good reading material on all this.
Actually, some of it he has already provided, which I'm yet to put up on the web. So that will happen in the coming days. Yeah. To look forward to that. And yeah, there are no questions or comments online. Yeah.
Okay, then.
Sure.
Thanks, everyone, for listening to my favorite subject. One of my favorite subjects, but yeah.
Yes. And thank you so much for putting in the time and effort for organizing this into this small series, and we look forward to, when we started talking about this, we had, I guess, maybe a somewhat grander, but something looking more closely at some aspects of radio interferometry or astronomy in mind as well. So maybe at some point in the future, we'll...
Actually, if there is, of course, we should now sample the population now that they know what kind of approach they might get.
Right.
Yes, you are aware, but maybe not the entire audience, that I had given maybe a larger number of lectures in Caltech in 2018 to that small radio astronomy group there. And polarization was only one lecture there.
Right, yeah.
So there were lectures on deconvolution, some lectures on electromagnetics, because I thought, it's good for radio astronomers to know that, how these telescopes work, especially the kind of low frequency array they had radiates over the entire sky. So there are some very interesting conceptual issues there. And I think I had one final lecture, which was radio astronomers and optical astronomers are schizophrenic. One group thinks in terms of fields and one group thinks in terms of photons. So is there a unified way of doing this? So yes, I do have ideas on all of this. And let me try and put something together and then see if there's enough interest. Okay.
Sure, yeah. Perfect. Yeah. Thank you so much. Thanks once again from all of us, not just the ones present online right now, but all the ones who will be listening to your lectures online and learning from them. Thanks once again. Yeah. Bye. Take care.
Thank you. Bye-bye.
Thanks. Yeah. Bye.